Good, good evening, guys. This is the second video. In the first video, I explained about the fundamentals of the mechanical engineering design. In the second video, I'm going to explain about the principal stresses. Okay. So, what is the need for going for the principal stresses? Why it is needed? Because in the first video, I explained about the basic fundamental stress, strain, and shear stress, everything. But apart from this shear stress, shear strain, stress and strain, we should be in a knowledge or we should be in a position to know about the principal stresses, why it is needed for the principal stresses. So see here in this picture or in this slide, say for example, two diagrams are there. One is direct stress in two mutually perpendicular planes. Another one is direct stress in one plane accompanied by a simple shear stress. In both of the cases, it is a rectangular body ABCD. ABCD. In the ABCD, we are having the sigma 1 is axial tensile. Here also is axial tensile. Both are axial tensile. Second case, here also axial tensile and here also one is shear stress. Okay, so first case no shear stress, second case shear stress. So totally combined loading, say for example single loading means, in the first video I gave the formula, but combined loading, more than one kind of loading means, so under that case it is not easy to solve the problem or solve the unknowns. So under that case this combination comes under biaxial, more than one axis. Okay, biaxial. So direct stress in two mutually perpendicular direction. Okay. So two mutually means here also one, here also one, mutually perpendicular. So under that case, two mutually perpendicular plus also shear, but the diagram it is not there. Three cases are, that means tensile sigma 1 and sigma 2, then shear also. Here also the first diagram is mentioned, shear tau. So three forces are there, or three kinds of loading is there. So three kinds of loading means definitely we need the help of the principal stress. So in the principal stress law, what is the first thing is, again loading 1, loading 2 and loading 3 tau, normal and shear stresses are obtained. So these normal and shear stresses are obtained with the help of the principal stress concept. Okay, so here same rectangular body ABCD of uniform cross-sectional area, unit thickness 1 mm. So subject to stresses as you shown in the previous diagram. So here, when you are solving the problem, normal stress is sigma T1 and sigma T2. That is a maximum principle and minimum principle, accompanied by shear stress tau also acting in the picture. Okay. So see here, the stress in a plane which is at right angles to line of action of force. While solving the problem in the principal loading, there are three planes, X, Y, and Z plane. In the three planes mutually perpendicular to each other, which carry direct stress only. So direct stress means normal stress. It may be tensile or compressive. No possibility of shear. So under this direct stresses will be occurred in the maximum principal plane or it will be in the minimum principal plane. So it may be noted that out of three direct stresses, one will be maximum, the other will be minimum. Okay. So maximum maximum tensile stress, the minimum will be minimum tensile stress. Okay. So here in the principal plane, there will not be a possibility of shear stress. Clear? So these principal planes which have no shear stress are known as principal planes, and the direct stresses along the plane are known as principal stresses. So first of all, what is in by principal plane? So in the principal plane, there will not be any possibility of shear stress. Only maximum stress or minimum stress. Two possibilities will be there. So the planes on which the maximum shear stress act are known as planes of maximum shear. Okay. So this is the case. So here the maximum shear stress formula is maximum principal and minimum principal. I already gave in the previous slide. So here tau max equal to sigma T1 minus sigma T2 by half of this value only. Okay. Here sigma 1 maximum principal, sigma 2 minimum principal, tau is the shear stress. So here application of principal stress is designed given that there are many cases in which machine members are subject to combined stresses due to simultaneous action of either tensile or compressive stresses. Then here, propeller shaft, C clamp, so all the cases there are direct tensile or compressive stresses and shear stresses due to torsion. So which may be direct tensile or compressive stresses. So this is the information about the principal stress and principal plane. At last, we are having the three formulas. Why I am given these three formulas is, these three formulas are enough for solving the problem for the maximum tensile stress. Okay. So sigma T max, that is sigma maximum principal stress. Sigma T means sigma T for tau is the shear stress. Okay. So sigma T max equal to sigma T by 2 plus half of root over square sigma T the whole square plus 4 tau square. Then maximum compressed stress sigma T max equal to sigma C by 2 plus half of sigma c plus 4 tau square. Then maximum shear stress tau max equal to half of square root of sigma t square plus 4 tau square. So here sigma t is mentioned very clear. Tensile stress due to direct work and bending. Sigma c is the compressive stress and tau is the shear stress due to the torsion. So whenever solving the problem, because in the next slide we're going to solve one basic problem. So the basic problem you should use the three formulas. Maximum tensile, what is the formula? Maximum compressive, what is the formula? Then maximum shear stress, what is the formula? So all things you have to design very clear. Okay. So that is information regarding the principal stress and principal plane. So here also one problem. It is one shaft. Say for example, in the shaft we are fixing on this end is arrested. Here is load. Not only this load, here tensile load is there, and what is called shear load is there. Rotational torque is there. So due to the action of torque and the tensile, what is the changes here? So practically you can see there, whenever apply this load, this bar will bend, the shaft will bend. So upper part will be tensile stress, lower part will be subjected to compressive stress. So what does it mean? At the point A, there will be a possibility of tensile stress, and point B will have a possibility of compressive stress due to this two load. Okay, so this you have to know and keep in mind. Other things they are formula based only. So you have to know the concept whenever applying the two loads, that is torque and the axial load. At the point A there is a possibility of tensile stress, the point B there is a possibility of compressive stress. Okay, so cross sectional area A equal to pi by 4 d square, and then tensile stress due to sigma c equal to p by A. Load is given 15 kilonewton tensile axial load by area, so 1.64 newton per mm square, that is megapascal. 1 megapascal equal to 1 newton per mm square, so we convert to direct terms of megapascal. Then due to this load, there will be a possibility of bending. Not only tensile stress and the bending. So M equal to W into X. So what is the for W? 3 kilonewton will be changed into 3000 Newton. So 3000 Newton into 250. Why you are having 250? This is the perpendicular distance. So bending moment equal to force into perpendicular distance. So 3000 into 250, 750 into 10 to the power 3 Newton mm. Okay. So here in the first part of the thing, we are having the tensile stress and the bending moment at A and B. Okay. Next thing is section modulus. For every shaft, we are having the section modulus. Section modulus, we are having the formula Z equal to pi by 32 into d cube. So pi by 32 into d diameter is the 50. So 12.27 into 10 to the power 3 mm per cube. Then bending stress at points A and B, because top point is A and bottom point is B, as already mentioned. So sigma B equal to m by z. M is given moment, that is given, so 61 point Newton per mm square, 61 point megapascal. The bending stress is tensile, as I mentioned at the start of the problem. The bending stress is tensile at the point A and compressive at point B. At the top edge A, there will be a possibility of tensile. At the bottom point B, there is a possibility of compressive. So resultant tensile stress at point A equal to sigma A equal to sigma B plus sigma 0. So that is 68.14 megapascal. So this is both are tensile. Why it is going to means at the point A, both are tensile. So we have to add algebraic sum sigma b plus sigma 0. But in the resultant compressive stresses, we are having this minus sigma b minus sigma 0. That's the difference in the case of the tensile stress and the compressive stress. Then after finding the tensile stress and compressive stress, we are having the shear stress. As I mentioned, due to the torque in the shaft, we are mentioning the torque also. So tau equal to 16t by pi d cube. So 16 into 1 into 10 to the power 6 by pi into 50. So torque is 1 into 10 to the power 6. 10 to the 6. Then diameter is 50. So 40.14 Newton per mm square. This formula already we are using in the design of shaft design. So in the shaft design, we are using the formula. Okay, so it's already discussed in the mechanics of solids. Mechanics of solids for having design of shaft, this using is formula. This formula is applicable only for the solid shaft. Okay. Then after finding this thing, stresses at point A. So maximum principal, minimum principal, then maximum shear stress. So 1, 2, and 3, these are applicable for the point A, because in the question it is asked very clear. Determine the resultant maximum stresses at the point A and B individually. So maximum principal plus minimum principal minus sigma a is the tensile stress at the point A. Sigma a is also, then here also sigma a, because we have to find out the value for maximum principal stress at point A only, we have to know. So sigma a max sigma a வந்து maximum tensile stress, tau is the shear stress. Okay, by putting the value sigma equal to 87.67 megapascal. Then sigma A minimum equal to 18.93 megapascal. Then tau max equal to half of sigma A plus 4 tau square. So that is the maximum shear stress. So every point here in the shaft we are having the 2 point A and B. At the point A we are having sigma A max and sigma A minimum, and shear stress will be tau A max and sorry, not point A. Similarly, we are having the stress at point B. We know that the maximum principal at normal stress at point B, sigma B max and sigma B minimum. So here at the bottom edge point B, so how much amount of force will be acting on sigma B max and sigma B minimum and tau B. So here also you want to substitute sigma B by 2 plus half of sigma B the whole square plus 4 tau square. Sigma B is 43.46 and 40.74 tau is the value. So 75.46 megapascal compressive. Then sigma minimum B minimum equal to half the sigma b minus half of this value, same value, so minus 22 is a tensile, 22 megapascal tensile, that is the minimum principal or normal stress. Then maximum shear stress tau max equal to half into sigma b plus 4 tau square. So these are all the stresses at the point B, because the question itself is asking very clear. You go to find out the maximum resultant forces at the point A and point B. Okay, so that is the case. This is the first problem. Here, second problem is the overhang crank with the pin and shaft. Here also one view is one view. So here mainly we're having this what is called axial load, tensile compressive load. So in the compressive load, a tangential load of 50 kN acts on the crank pin. Maximum principal and maximum shear acting on the center of the crankshaft bearing here on the center point. Okay. So all the values are given. Here you note one parameter y value. Y is 140 and x is 120. Okay. Y is the perpendicular distance of this load. 120 is the parallel load, so that you keep in mind. So bending moment at the center of the crankshaft bearing. So m equal to w into x, 15 into 10 to the power 3. What is the value? 120 is the perpendicular distance. The torque equal to w into y. Torque equal to force into distance or force into radius. Radius means it's a diameter by 2. So that is a 15 into 10 to the power 3 by into 140 is the value here. So bending stress sigma b equal to m by z. 32 m by pi d cube. These formulas we discussed in the mechanical solids 30 unit design of shaft design. And what is the value of 35.8 megapascal? Then shear stress due to torque tau equal to 16 by pi d cube. That is the 29.20.9 megapascal. So once you calculate the basic parameters, then again going to the maximum principal, minimum principal, then shear stress, as we repeat the same procedure for the previous, what is in the previous problem, what are the procedures we repeated, same thing we repeat one more time also. So maximum principal sigma t is already known. This value 35.8 sigma t tensile stress is there. Then half tau square value is 20.9. So by putting these values, you are getting the maximum principal stress 45.4. Then is the maximum shear stress. We know that the maximum shear stress tau max equal to half into square root sigma t plus 4 tau square, 27.5 megapascal. So whenever the principal stress problem, in all the problem, basically what you should be in a position to find the maximum principal and the maximum tensile stress and the maximum shear stress. So these are all the three parameters you got to find in all the principal stresses and principal planes. Okay. Then the next one is the theories of failure. Theories of failure is everybody known. What is the need for going the theories of failure is nothing but theories of failure means whenever going to design a component, it should have the some maximum value. So above the beyond the maximum value, we cannot operate the object. So when you're going to design the component, we have to design the component based on the allowable load. Okay. So beyond the allowable load, we can operate the component at a safe condition. Beyond the operating load, beyond the value, we cannot operate the value. So theories of failure under static load. Five theories: maximum principal stress theory, Rankine theory; maximum shear stress theory, Guest theory; maximum principal strain theory, Saint-Laurent theory; maximum strain energy theory, High theory; last maximum distortion energy theory, Henke and von Mises theory. Okay, so these are all the things you have to note from the thing. First theory is the maximum principal normal stress theory. Sigma T1 equal to sigma yield by factor of safety for ductile material, sigma U by factor of safety. So it is a possibility of failure due to ignoring stresses. So brittle material which is strong in shear but weak in tension or compression theory is generally used. So this theory is applicable for both the tensile ductile material and the brittle material also. But in the ductile material, sigma yield, sigma y, we have to put the formula. Here sigma u got to put the formula, that is for brittle material. Okay, so this is the first theory. Second theory, maximum shear stress theory or Guest theory. So here mainly we are dealing with the shear stress. Okay. So is equal to the one of the yield stress in tension only. So 1/2 is 1 by 2 into sigma VT by 2 into factor of safety. So tau max equal to maximum shear stress, tau shear stress the yield point, factor of safety. This theory is mostly used for members of ductile material, because in the previous theory we can apply for the ductile material as well as brittle material. Here also mostly it is suitable for opted for ductile material. Third theory is the maximum principal strain theory or strain tolerance theory. So sigma max equal to sigma T1 by E minus sigma T into M into E, where M is the 1 by M equal to Poisson ratio, E is the Young's modulus. Sigma T1 and T2 are the maximum minimum principal stresses, factor of safety. So this is also the maximum principal strain theory. This is in general, it gives only reliable results. Okay. So whenever the component involving strain, under the case, we're going for the maximum principal strain theory. Then maximum strain energy theory, Hayes theory. So we know that the strain energy per unit volume in the biaxial system, U1 what is the value, U2 what is the value. So 1 by 2 E, U1 equal to U2 1 by 2 E, sigma T1 tensiles, and tensile in the sigma T1 is the tensile stress, and one direction, the other x direction direction, and sigma Y to yield strength by factor of safety. So this theory may be used for the ductile material. This is mainly related to the strain energy. So whenever the component involved design of the strain energy, we should be taken into that maximum strain energy theory or Hayes theory. So maximum discharge energy Henke's theory. So this theory is mostly used for ductile material in the place of maximum strain energy theory. The maximum discharge energy is the difference between the total strain energy and strain energy due to uniform stress. So this is the last thing. Here it is sigma T1, here sigma T2, then sigma Y2 by factor of safety. So this is the theory. So maximum discharge energy theory. So these are all the 5 theories of failure. So in the first problem, in the bolt problem, two loads are given. Axial pull is given, transverse shear force is given. So with the help of the diameter of the bolt, you have to find the diameter of the bolt as per the 5 theories. Okay. So here cross section of the bolt A equal to pi by 4 d square, and pi by 4 d square diameter is the, in terms of diameter you got to find axial tensile sigma 1 equal to pt by n. So 10 by 10 is the axial pull divided by this 0.7 per d square. You got the equation in terms of d square. Transverse shear is nothing but what is the value, 5 shear force of 5 kilonewton divided by area. This is the thing. So in all the formulas you will find sigma t1 and tau. Okay. In some cases you can use the power called sigma 2, because it is a here in the problem axial pull, one axial pull is given, there is a one direction. So in some other problem, so in the next formula we can use the value for sigma 2. What is the value for sigma 2, I'll explain at the time. But in the axial tension, the sigma 1 and tau should be compulsory. This you compulsory, you should be the formula. So according to the maximum principal stress theory, we know the maximum principal stress sigma t1 equal to sigma 1 plus sigma t by 2 plus half of sigma 1 by sigma 4 tau square. So here sigma 2 is 0. As I mentioned, clear, only one direction acceleration is given. Sigma 1 is given. There will be no place in value of sigma 2. So similarly, tau is given. So by putting these two values, you get the value for sigma t by 2 plus half of sigma t by 4 tau square. So this is equal to 15.365 d square. So according to the maximum principles theory, sigma t1 equal to sigma 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 t the reference, then the value is the maximum level is 100. So diameter ED equal to 12.4 mm. This is the value we got from the first theory of the failure. Second, maximum shear stress theory. So actually this is suitable for the shear stress option. So tau max equal to half of sigma 1 minus sigma 2 plus 4 tau square. Sigma 1 is already mentioned and sigma 2 is 0 because it's a single loading biaxial. It is not a case of the biaxial loading, single loading. So all these things you can put in the formula. Then the d square equal to 13.42 mm. Then, according to the maximum principal strain theory, because this is a maximum principal strain, this stress by strain. So, first two theories are related with the stress theory, Rankine stress theory and the shear stress theory. Here we are now having the principal strain theory. So, sigma T1 equal to sigma 1 by 2 plus half of this value here. The minimum principal minus half of this value here. So, by putting the quadratic equation minus 26.5 by d square, then this value, according to maximum principal, this will be equal to sigma T the allowable value. That is a maximum value. So from the maximum value, you're getting the quad equation. From the quad equation, you're getting the value for the diameter D equal to 12.7 mm. This is the value we got from the maximum principal strain theory. Then according to the maximum strain energy theory, so here also sigma T1 and sigma T2 is 0 and so minus 2 to this whole time will become 0, then allowable value. So this thing you have to think is we get an equation in terms of d power 4. So from the equation that d power 4, we get the value for d equal to 12.78 mm. So that is the value for the maximum strain energy theory. Last theory, according to the maximum distortion theory, so here sigma T1 square plus sigma T2 square minus 2 T1 and sigma T2. So here apply all the values, and finally you can get the value for diameter in terms of d power 4 chord equation, then d equal to 13.4. So every cases you're having, they determine the this question is asked very clear. Determine the diameter of the bolt according to the various theories of failure. So from the 5 theories of failure, which is the maximum value, that maximum value could take as a best design in the case of the diameter. Suppose in this problem it's not asked. In some other problem, you have to choose the best design or to choose the maximum diameter of the object. Another case, we have to follow this method. Okay, so there is a in this thing we are going to explain the I explained the principal stress and strain and the problems, and the what is the formula of failure stress? That is a theories of failure. So theories of failure, we're having the five theories, and apart from the theories, we solved one problem, basic problem. Okay, so thank you for your understanding. Then thanks for the thing. Then remaining thing I will give in the next video. So we will see in the next coming videos. Thank you, thanks a lot.